As I was finishing to add the last editing touches to my previous video, I randomly remembered something about the problem, namely, that it had been listed along with other difficult problems by many prominent mathematicians of their times. Looking at one of those lists, I started thinking about another of those unsolved puzzles, and a thought occurred to me. This is what I'd like to show you today. I'm thinking of doing this exposition a little differently this time. To begin with, I will strongly recommend that you watch my other video first, as it will make everything much easier to grasp. Also, I think I'm going to shake it up and do things slightly out of order this time. I'm not going to pretend that I know what I'm doing, but I feel like experimenting with presentation. So, apologies in advance if it's confusing or simply falls flat. Okay, you remember how I decomposed the previous problem into some kind of a grid, right? This time, I'm going to give you the grid first, then we'll talk about the actual problem. Here goes. The first row refers to modulus 2, so it's about the parity, and starting from the modulus itself, we are going to reject odd numbers. What can I say? They are odd, aren't they? Okay, got it. No more dad jokes for me. Moving on. Next, we will add one row for each prime of the form 4k plus 1. The first one is thus for modulus 5, and starting from the column matching the modulus, we will reject the two quadratic residues minus 1 modulo 5, which happen to be 2 and 3. You might be asking yourselves, why did we jump over the other primes of the form 4k minus 1? Very simple. There are no quadratic residues minus 1 modulo p with those guys, so we don't need to worry about them. Next in the list is modulus 13, and the residue classes we want to exclude here are 5 and 8. And so on. Alright, let's collect the survivors and see what we got. Now, if you plug these 14 first numbers in the search bar of the OEIS website, you will get one single hit, namely, sequence A5574, the sequence of numbers k such that k squared plus 1 is a prime number. The generic name for these numbers is near square primes, and there are different varieties of them, but it was this precise class, those of the form k squared plus 1, that were of interest to Edmund Landau when he listed 4 fundamental and unanswered questions about prime numbers at the 1912 International Congress of Mathematicians in Cambridge. We were indirectly working on the third problem in the previous video, and this time we're looking almost directly at the first one. Alright, history is nice and all, but what's the story here? Can we perhaps do the same kind of rough estimation like we did before? Well, the domains aren't as nice and tidy as they were in the previous video, but maybe we can manage? Let's see. If we take our boundaries to be the subset of primes in the residue class 1 modulo 4, then we can define adjacent ranges of integers like so. The sizes of the j sub n sets are a little all over the place, but as n grows large, we know that they will be of order log of n. The corresponding densities need a factor 1/2 for the modulus 2 component, and a product over primes which should look somewhat familiar. And due to the fact that we're using only half the primes, we end up with a different asymptotic. In the end, we estimate that as n grows large, every j sub n range will contribute, on average, a constant number of new elements to the capital S set. Sounds very promising, doesn't it? Since you've watched the 6ab plus minus a plus minus b video, I'm not going to repeat the next steps in detail, but in a nutshell, they consist of: first, answering the question, does the Granville-Kurlberg theorem apply? For the record, I think it does. Second, calculating the probability. For the record, I found that the probability that we stop finding new elements of S tends to 0. However, this is trickier this time, and you'll need good asymptotics in order to show that it does. In particular, this constant better be greater than 1. And finally, drawing a conclusion. Mine is that, indeed, there are almost certainly infinitely many near-square primes of the form k squared plus 1. What is your conclusion? Let me know what you think in a comment.